I forgot to do that earlier. Yeah. So, okay. What I'd like to do now is kind of look at page 55 and start talking about chapter 10. So I'm going to screen share just so you've got it. And let's go to here. And all right. So we're getting into some interesting stuff. It's pretty important that you understand these symbols and units. And chapter 10 is the toughest chapter in this course. So you've got your work cut out for you. You're going to have to go through this, watch some videos, do some problems, and just keep going around. Let's see if we can go through this stuff. Hopefully your page looks a little bit like mine. Again, page 55. So theta, strictly speaking, it's not a vector, but we could treat it like one for this course. So theta is going to be called angular position. Delta theta, that's angular displacement. So just like we had x was position and delta x was displacement, same thing. When we're doing problems, usually we use radians for this. The reason is radians are used in calculus. And so sometimes our problems require calculus. Excuse me now. Omega. Okay, we've talked about that before, but that's just d theta dt. That's the rate of change of the angular position or angular velocity, and that's in radians per second. You can think of that as RPMs or revolutions per minute. Radians can be converted to RPMs, and you can see here, take a look. This is a good equation to remember right here. Hopefully you see that highlighted on your screen. 1 radian per second, when you do the math, basically is 10 RPMs. So yeah, it's not exactly right, but just think it's about 10. That works out for checking your work. Okay. Alpha is the symbol we will use for angular acceleration. So obviously that's going to have another time in the basement. So we take a derivative and then we take another derivative. We get radians per second squared. Period, I'm going to write like this. That's the time for one oscillation or one revolution. F is the frequency in hertz. So frequency is basically how frequently this thing rotates, whatever this thing is. So if something is rotating at a certain frequency, that's how many rotations or revolutions per second. So hertz is right here. These are all the different ways you might see hertz written. Hertz, seconds to the -1, or sometimes revolutions per second, or even cycles per second. Those are all the same thing as frequency. So watch out for this. There's frequency, F, and if you recall earlier, angular frequency was omega. So there's F and there's omega, and I think somewhere down here, do I have it? I don't know where I've got it. So I'm just going to scroll up here. Oh, right here. Sorry. Here it is. So in this case, there's a difference between the radians per second and the cycles per second. So obviously, if you have 1 revolution per second, you multiply that by 2 pi to get about 6 radians per second, something like that, 6.28. Now, just like before, we had kinematics. We could use the same equations. Look at these. Anytime, whoops, this is like A, right? It's not quite the same. This is like V, and this would be like, I guess, V final, and this would be like V initial, right? You could think of it exactly the same way. This is delta. This right here is like delta X, V initial X, 1/2 AX T squared. Same equations. Now, before we get too crazy, I want to point out, strictly speaking, theta is not a true vector. As long as we restrict ourselves to one plane, then we're true. So we could treat theta as a vector. So we could treat theta as a vector as long as the object's axis of rotation remains fixed. So if we have a record player and it's spinning a record, or if you have a ball that's spinning or a bike wheel that's spinning, as long as you don't change the axis of rotation, we're going to treat this thing like a vector. All right. And just like before when we did kinematics, watch out. These could be plus or minus, right? So this number right here could be plus or minus. So could this number. So all the same tricks that came up, so could this number, right? Time we're going to assume is positive though. But yeah, you can get positive or negative signs here. And just like before, watch out for questions if I say angular speed versus angular velocity, or if I say magnitude of angular acceleration. So just the same tricks that we've been doing all before. All right. I'm just going to check the chat somewhere. I think we're still good. All right. Okay. And this is one of the more confusing parts about rotation. So when you look at this one, I'm looking at this picture at the bottom of page 55 still. This thing is clearly rotating, whatever this is, something is rotating this way, okay? The rotation rate, we would say it's going counterclockwise. According to physicists, we're going to say it's rotating k hat. Just in case my mic was cutting out, I'm going to say that again because it's pretty darn important. In this case, and I'll even stop the share for a second. All right. So in this case, you line up your thumb with the axis of rotation. So in this case, if it was coming out of the page or whatever, you could say that would be a k hat. Oh, geez. I think my camera is flipping left, right too. I could check that really quick. Just put some text up here and see. Oh man, is that flipping the text? Yeah, it is, right? So, okay, this is gonna be, man, I can't do this. Yeah, basically, you're just gonna have to believe me here. You put your thumb in the direction of the axis and use your right hand. I'm not using my left hand. I'm not trying to lie to you. And so then when you do that, you line up your thumb with the axis and you twist your hands. If your fingers are curling the right way, then your thumb would be out of the page and you have a rotation, say positive k hat. If it's going into the page, you could get a negative k hat. Let me get back to that screen share. This is a particularly awkward thing to try and do when we have all these images being flipped left, right. So in this case, just look at this one. If you put the fingers of your right hand and curl them around counterclockwise, just put them on your piece of paper and curl them around. I hope you see your thumb points out of the page. That's why we call it out of the page. Yeah, and there's a question there. Clip this for Eston, the right hand thing. I'm not sure what you mean. Oh, okay. So Zoom flips the image. I see, but okay. So hopefully that was working then. And then I'm not sure if Eston's sharing his screen there, but yeah, that'd be cool. Okay. Yeah. Let me see. Eston, did you have a good picture? Is that the deal? If you did, that's cool. And you could send it to me and I'll send it to everybody or whatever. I'll get back to this. Looks like there. Okay. All right. You're good. Whatever. Okay. My bad. All right. Back to it. So in this case, if you want to follow these rules, you could do that. Maybe you could watch a YouTube video for right-hand rule if you want as well. Now, in physics, this is where we get even more annoying. If everything in a problem is rotating clockwise, sometimes I'll change my mind and say clockwise is positive. And then, yeah, I'll explain that later when we get to the last half of chapter 10. That shows up in the last half. And then let's get done with this page so we can do some problems, all right? S is called arc length. And if you wanted to figure that out, if you know the radius of something, so if I could go up here, and I'll get your question in just a second, Ryan. In this case, look at this red line right here. This would be the arc length. It's the distance traveled along the arc. It's the length of the arc. In this case, it's the radius here, radius, times delta theta. So here, S is equal to the radius times the change in angle. Now, you you might recall that earlier I said you have to do this in radians, and this is why. If you plug in degrees here, it doesn't work. It must be in radians. So if we're going to take this, think of the circumference formula, right? C equals 2 pi r. In that case, the arc length all the way around is 2 pi r. Well, 2 pi is the radians. So it's got to be in radians. Oh, man, I hate this Zoom crap. All right, Ryan, go ahead and speak up.
I got it. I got it answered.
Okay, cool.
I was just curious about you said we call it rotating counterclockwise K. I was wondering what the alternative was, but it's negative K because it's going into the page.
Yeah, exactly.
Okay, that makes sense.
So you're either going positive K hat out of the page or negative K hat there.
Got it.
Yep. And that's cool. All right. So good question. So this one we already know. V, it's not your omega, it's our omega. Now here's a new one that we maybe, I think we alluded to this earlier in the semester when we were talking about the swinging pendulums. When we talked about swinging pendulums, we said that the tangential acceleration relates to this angular acceleration. Or I think we talked about A-tan, but now you can see how to get that. So if you know that, okay, that's cool. A centripetal, there's two ways to write that. And this one ends up being the most useful, this R omega squared. So it just ends up being a little bit easier to work with for chapter 10 problems usually. And then if you recall, if this thing has some centripetal, and I'll try and draw on this picture here for a second. Let's imagine that we had a ball here. You could imagine this is a ball on the end of the string. There might be some tangential acceleration. We could say A tan this way. That's an acceleration tangent to the circle. And there might be some component here towards the center. That would be AC. And then by the parallelogram rule, we know that this sucker right here is A total, right? So the total acceleration is not necessarily toward the center or parallel to the edge. It could be off at some random other angle. I hope that you will see this in lab next week. This week, we're going to do center mass in lab. Next week, we're literally going to be doing the lab on trying to understand rotation motion and understanding this chart. So this chart you're going to work on in lab next week, all right? And so if you get ahead, you could actually do that in lab this week and then have more time to study. But yeah, whoops, a couple of last things. Notice if you go, okay, so two things here. This one, the magnitude of total acceleration, obviously it's going to be AC squared plus A tan squared, which when you plug that in, you could actually factor out an R because they each have an R. And I think you get omega to the fourth because it was omega squared. So watch out for that little trick there. And again, these are only going to make sense if you're using radians. If you have degrees per second, excuse me, sorry about that, it's not going to work. All right, and check this out. Because S is equal to R theta, V is our omega, and A tan is our alpha, take a look at this equation. If you multiply that equation by R, multiplying by R gives you arc length, multiplying by R gives you velocity tangential, multiplying by R gives you A tan. That's this equation. And you could do the same thing for these other ones. So if you want to talk about an object as it translates around the edge, you could use these equations. If you want to talk about an object as its angle rotates, you could use these equations, and they're equivalent. They're related by a single multiplicative factor of R. Whew, that's a lot of stuff there. So I'm going to pause for a second before we go on and see if there's any questions here. It's like the most boring way to teach, huh? Sorry, everybody, that it's not very exciting. This is a weird time to be doing physics, right? Pretty bizarre. Anyways, let's get to it. Just confirming. Okay, looks like everybody's good. And yeah, sorry if I'm not reading you very well. It's really hard to read everybody and do all the screens. So I'm sorry. Let's just start simple. Let's do 10.1 together, everybody. Let's look at 10.1 on the top of page 56. And let's use this. And there's a chat. Just like kinematics, but yeah, only legal as long as the axis of rotation doesn't change. Yeah, something like that. All right. Yeah, let's look at 10.1. And of course, none of you actually know what a record player is anymore, unless you're a DJ, but maybe DJs don't even use records anymore. I don't know. But yeah, so I'm looking at 10.1. Let me just get it up on screen for everybody. And it should be the next one. All right, so we're looking at this one right here, 10.1. All right. And hopefully you have the questions out in front of you. What I would like to do is just go straight to the solutions on this one and walk it through it and see if there's any steps that don't make sense. So 10.1, let's use this one as a worked example and just go through it together. So we're going to try and get the magnitude of angular acceleration. That variable is obviously alpha. We're going to get the magnitude of total acceleration. Now that one is going to have units of meters per second squared because it's an acceleration. Part A is angular acceleration. That's going to have units of radians per second squared. There's a difference. And then the total distance traveled. Total distance traveled is arc length. All right, so let's pop over into there. You can keep the question in front of you if you want. I'm going into there. Whoa, that's a little heavy. All right. Whoops. So here we go. Now, in this case, I did a couple of conversions. And so notice in the problem, they tell us it's 33.333. That's enough sig figs, I'm sure. Revolutions per minute. And so I know that if I'm doing a kinematics problem, I want to use units of radians per second. So you do a quick conversion here. So you got 1 minute is 60 seconds. And then you're going to say 1 rev is 2 pi radians. And then if it helps, I know it's not exact, but 2 times pi is just about 6. It's 6.28, right? 3.14 times 2, 6.28. And so notice, let me change colors really quick. This number is 60. This number's about 6. I'll say 6-ish. And so it should be effectively dividing by 10. It's not perfect, but notice this was about 33 and this is about 3.3. It's not exact. So usually I just keep that in mind. It should differ by about a factor of 10. Going from radians per second to rev, you multiply by about 10, the other way. Okay, good. And so now in this case, I made some assumptions. It doesn't tell us which way the record player is initially rotating. So if it doesn't tell you, why not assume it's initially positive? So I made this assumption. I assumed it was rotating positive. That's an assumption. As a result, this equation now makes sense. Okay, all I did was I took the angular kinematics equation, V final equals V initial plus AT, except now it's omega final equals omega initial plus alpha T. I solved that for alpha algebraically. Because omega final is 0, and because omega initial is about 3, we get this interesting result. Don't forget T was 10 in the problem. All right. And then, in this case, did I ask for the magnitude? Oh, because I asked for the magnitude, that gets rid of the minus sign. Oh, what a sneaky, sneaky punk I was. All right. So that's that one. Next, in part B, it says determine the magnitude of total acceleration for the point on the rim 2 seconds before it comes to a stop. Okay, I want to use A total equals this. This is the equation I want to use, but I need to know both omega and alpha and R. In this case, alpha is the number from right here. I know what alpha is. Omega, I'm going to have to do some math to figure out omega. So I'm going to use this equation. I'm going to plug in 8 seconds because I was 2 seconds before the end. That's 8 seconds total. I can plug that in and I can get omega. Once I have omega and alpha, I look back in the problem and I think they told us the radius was 0.24 meters. Yeah. Yeah. All right. That's cool. And so then it's just plug and chug. And again, we're trying to get the magnitude. And yeah, you could get that with a ratio if you really wanted to. All right. And then finally, in part C, you could do this in a couple of different ways. Here's the way that I chose to do it. Because I know what alpha is and omega initial already, it's pretty easy for me to get delta theta. And notice I got it in units of radians. If I do that, remember that radians times anything is unitless. So 0.24 meters times whatever delta theta was, 17.46 radians. The units of it are going to be meters times radians. Meters times radians is just meters. So that's why we want to keep this in radians all the time. If you need to suddenly slip into kinematics, you can go back and forth as long as you're using radians. But if you're using degrees or revolutions, you cannot do that. So that was 10.1. I'm going to pause and see if there's any questions here and bust out the chat. Okay. What do you think? Any questions? You guys are all oh, go ahead. Yeah.
On that last, not very last, but close to last part, you found omega, you were saying, to plug into the equation by using the other rotational kinematics equation or angular kinematics equation?
Yeah, so right here. In this particular case, we know omega initial and we know alpha. And the problem tells me 2 seconds before the end, which tells me, well, that's 8 seconds because the total time was 10.
Okay.
So between that, I know all 3 pieces. So that's the easiest way to get omega final. And
Right.
that's what you
Okay.
needed. Is that what you needed?
Yeah. Yeah. And then we were given R, we have omega, and then we just found alpha. So then we just find A total.
Say again.
So we were given R in the problem, and then that way we found omega and we knew alpha, and then that way we just find A total.
That's right. That would be A total. Yep. And again, if the problem had said it was rotating, say, clockwise, then you could say it was B, a negative omega initial or something. But yeah.
Okay.
Unfortunately, I think in this problem, it doesn't matter because all of the answers were magnitudes. Look carefully at parts A, B, and C. If we had said, well, wait, I think it's going the other way, you should still get the same magnitude of alpha. You should still get the same magnitude of A total, and you should still get the same distance traveled. It might be traveling in a different direction, but in this particular case, it should all work out. So I'll stop there. Yeah. So that's, I guess, why I asked for the magnitudes, because then we don't need to know the rotation direction. That was clever. All right. Let me do that.
I just had a quick question.
Yeah, go for it.
So at any point would we have to use centripetal acceleration for the beginning part of chapter 10?
Yeah, actually. So remember, I'm going to write in the chat. So
Okay.
that's a different way of doing it. Whoops, come on now. You could say it like this. And so that's basically what I just did, Angel. I took the square root of A centripetal squared plus A tan squared.
Okay.
And if you want take a look at question 10.2 and 10.3 actually directly ask you to plot AC versus time. And so there's some times where I'll literally ask, what is AC?
So you'll differentiate for us in the questions what you want.
Yeah, in these types of questions, I try to be very clear if I want a total, a C, or a tan, or alpha, which is angular acceleration. And I think actually the math on this part, you're going to be pretty fast at and you're going to pick it up, but it's the wordings of the question that you have to pay extra attention to now, because we've got what, AC, a tan, a total, alpha, four different accelerations I could be asking about. And then you've got velocities and speeds and angular velocities and angular speeds. So there's four different, basically, angular velocity or velocities you could be asking about as well. It's gnarly. Read carefully, I guess is what I'm saying. Is that good, Angel? Angel, excuse me. Okay, got it. Okay, cool. All right. So just to show you how tricky this can get, basically you should do all of these problems between 10.1 and basically everything on page 56 and 57 is good stuff to do. I'm going to try and look at 10.2 with you right now. This is a pretty good one. I actually wrote this when I was living in Taiwan, so it's kind of fun for me. This was 10.2 and 10.6 were both these two train rides I was taking in Taiwan. So if you could imagine some nerdy physicist writing down questions on the subway, that was me. Anyways, yeah, let's take a look at it. I'm going to share the screen. And let's get into it. So here it is. Before you look at the solution on this one, see if you can correctly identify what crap I gave you. Going back to Angel's question, it's like you have to be very clear. Did I give you speeds? Did I give you angles? Did I give you velocities? What? All right, so let's take a look at this one here. Okay, you've got a train. It's starting from rest at Central, and it's going to Sanduo. The train speeds up at this rate until it reaches this speed, and then it continues. So in this case, what is that? Think to yourself, what did I tell you? Is that alpha? Is that a total? Is that a centripetal? Is that a tangential? Or is it whatever else I forgot? And then this one, you could think, what is that? Because if we don't know those things, we can't get anywhere. When you see these weird words, what does that mean? I'll give you a second, and then I'll bring up the solution. Get a quick drink. Okay, so I'm going to pop it up. Hopefully you thought that that was A tangential, and this is V tangential. So the 1.4 is actually the maximum recommended translational velocity for trains from some weird subway website I read. So if I could go down there to that one, you're hopefully identifying that as A tan. This is V final, the radius. We don't know the angle. Now, I do know this. Take a look. I do know omega final. How did I get that? I took V final and divide by R. If I divide by R, you can get from V to omega. All right. And then in this case, you can also do the same thing with A tan and divide by R. And it looks like I wrote it in units of milliradians per second squared, but whatever. Okay. And so for me, you can see I like these angular kinematics. Oh, I guess you could see that right here. as well. That's another way of doing this one. Here, this one goes to 0, right? So, yeah, you could do all kinds of stuff here. I don't know, whatever you want to do. If you don't want to solve it this way, you could go ahead and plug it with these values and stick the numbers in as well. But hopefully you get 67 degrees or so. So let me clear that out just a little bit. If you're wondering right here, do you agree that omega squared, well, if I know V equals omega R, it's not your omega, it's our omega. So V squared is R squared omega squared. And so from there, hopefully you see that we could rewrite that one this way. And notice alpha, we know that A tan is equal to alpha R or R alpha. So that's how I got this result right here and this result right here. It's all the same crap. You could solve it any way you want once you know the numbers. So it is good to check the units. Whenever you're doing these problems, check the units. This is meters per second squared. So meters squared per second squared on top. And then on bottom, we have meters. And then A, this is not radians per second squared. That's an A. That's meters per second squared. And notice the meter squared drop, the second squared drop, and we get no units, which in this case, no units, it would make sense to write it as radians. All right. And obviously, if it's accelerating for that period of time or for that amount of angle, it must be a constant speed for the rest of the time. Okay. And so I'm going to go ahead and look at the question again. Okay, so that was part A. The hard part is basically making sure you write down this crap, because once you get that, the rest of the question pretty much works out. So now it says, figure out the elapsed time. Well, I could go back and use my kinematics equations again, I bet. So here's one kinematics equation. Notice I use translational. That's fine. So if I know the velocity at the end of stage 1, that's the velocity initial stage 1 plus this. So I can do all that and I get a time. For the second stage, I used rotational kinematics for the second stage. Why? Because I know all the rotational variables from part A. So you could use either one of the kinematics equations. I chose the arc length version up here for the first stage, and I chose the angular version down here for the second stage. And then there's some weird note, whatever. Okay, that's cool. So depending which way you do it, you might get different sig figs, but whatever. All right. I'm going to pause right there, and let's go back here. If you have any questions, throw them in the chat there. It looks like you're doing all right, but if you have any questions, go ahead, throw them in. Hopefully kinematics, this is like a nice relief. I'm going to go back to it. If you have questions, throw them in there. So part C, what was part C? Oh, sketch plots. Now you guys can do this at home and sketch the plots. I think you learn a lot by sketching the plots. And if you don't want to sketch the plots, well, I know you're going to do it in labs. So, but I recommend trying to sketch the plots, or at least reading the plots and trying to understand them. If you don't have the time to sketch them, because I know you're busy and this is an awkward semester, you should at least look at them. And so let's take a look at these things first, or try and take a guess. A tan versus T. Well, this is A tan until you get to max speed, and then it drops to 0. So hopefully you could guess what that one should look like. Let's go look at it and see. I'll see if I can not give it all away. Oh, whoops. Oh, crap, I did. All right, let's go back. Okay, so AC, A tan, that's going to be a flat line that drops to 0. AC, let's think about that one for a second. AC is, you could think of it as V squared over R, or you could think of it as R omega squared. Either way, the initial velocity is 0, or the initial omega is 0, the initial rotation rate. So it's initially 0 velocity. It should have initially AC equals 0. And then because it's got a v squared over r, or a r omega squared, it should be squared. It should be a parabola. Until you hit max speed, it should flatten out. So now let's go look at these. It looks like I reordered this question, but I don't understand what I'm doing there. Maybe I skipped a step. I apologize. But here's what those plots look like. So here's that A tan, right? Initially, all of the total acceleration, so the purple is the total acceleration. It's almost all A tangential until you start speeding up. Once you start speeding up, we see that, oh crap, this red term really jacks up. And so the AC becomes a dominant factor as you get faster and faster. So as long as this builds up speed long enough, A tangential eventually becomes negative. You may recall early in the semester I said, oh, if we speed up very gradually, we're going to assume A tangential is negative. And that's because if A tangential is very small, this crossover is going to happen sooner. So, all right, that's cool. So anyways, yeah, and we get this unusual thing where once it gets to max speed, all of a sudden the acceleration is going to drop a little bit. So this is very unusual because right at this point, AC is constant. And then because this one drops to 0, all of a sudden the total acceleration also drops down and becomes just AC. So Angel, I think you asked a little bit about AC and ATAN. Is this maybe helping? You could throw it in the chat if you want. If that's helping you with your question from earlier, that would be cool. And then anybody else that has a question, feel free. All right. Oh yeah, I did do these things out of order a little bit. So if you want, you could figure out the magnitude of the force. Remember, if you want the net force, it's going to be A total. Okay, so A total. And then part E is for fun. You could think about this. If you remember part E, you're supposed to be thinking about fictitious forces. So in that case, remember that whichever direction you're accelerating, you could think of that as causing a fictitious force the opposite way. So when you have AC, there's a fictitious force to the outside of the turn because you're being pulled to the inside. Again, when you have AC, there's an acceleration towards the center, which means in real life, there must be a force towards the center. The seat or the subway car is somehow pushing you towards the center, but you perceive that as being pushed to the outside, a fictitious force to the outside. Same way, when you're accelerating forwards, when the train is speeding up, you have a tan. And so if there's an acceleration in the forward direction, you perceive that as a force backwards. So if you want, you can read question E and work on that on your own. All right. If you want, you could look at question 10.3, and that shows you how we might get a graph involved. If you remember, we're basically redoing, by the way, chapter 10 is redo chapters 1 through 9 in one chapter, but add in rotation. It's crazy. It's crazy. So we did graphing. This shows you an example of how you could use the graph. So let's take a look at 10.3 really quick. I'll bring it up in screen share. And, you know, I wish there was a better way to do this, but I'm trying to do the best I can. So hopefully it's good enough. And if it's not, I really apologize. This is not fun for anybody. So let me go to 10.3. And if you want, I'm going to check out, I think you could tell me if you want me to go faster or slower or whatever, or just dump in the chat. I know how to use the chat a little bit. So if you want me to go faster or slower, or if it's about right, you could feel free to add comments in the chat. So yeah, that said, I'm going to plow ahead with 10.3 right now. Okay. So imagine we have a turntable or a disc. If you remember in class, we had that demonstration where we had a large spinning disc and I put some stuff on it and I said, which one falls off? That's what a flywheel is, just a big metal disc that's spinning, okay? So don't overthink it. It's just a spinning disc. And here you'll notice this red line. Sometimes you'll see me do these dotted lines. That's supposed to indicate the axis of rotation there. So, and this is my way of saying it's rotating. So this is a way to represent the variable omega. By the way, W is weight, capital W with the pointy is work, and the curvy W is omega. Okay, so try not to say W. This is actually omega. Okay, so there's that. And what we're going to do is we're going to put some super glue on here and attach this block on here. So that way we could talk about this block. Okay, and this is 15 grams. So we've got a mass of 15 grams sitting out there super glued to the wheel. A plot of angular velocity versus time. Okay, so we're doing omega, and it says angular velocity, not speed. That's why it could be both positive or negative. So we got velocity, it could be positive or negative. And initial angular position is 0. So angular position, that's theta. Initial angular position would be theta initial. And this is 0. So they're just telling me that theta initial is equal to 0. Okay, cool. Now, okay, let's see here. At what time does the mass return to its initial position? Okay, this is a good one. So we know its initial position is 0. And we're asked, when does it return to that? So we're saying, another way of saying question A is, when does, sorry, I'm slow, theta final equal, in this case, theta initial, which we said was 0. I don't know if you could see it, but try to think back to chapter 2. All right. And maybe if I wrote it this way, if theta final equals theta initial, what is delta theta? Think to yourself or chat with a neighbor. Hopefully you thought, oh, well, delta theta is 0. Hopefully you're thinking right now, oh, wait a minute, the area under the curve. If I do the area under the curve, that's delta theta. Just like the area under a VT was delta X. Again, the area under a VT, so if you had a VT plot, if you have a VT plot, the area was delta X, right? So now, that's supposed to be a V. So now if I have an omega plot, the area would be delta theta, and I hope you could see it's at 4 seconds without having to do any calculation. We have the same positive area and negative area, so at 4 seconds, it should return. If you don't like that, you could say theta final equals, or whoops, sorry, let me clear this. We could say it this way, delta theta is equal to omega initial times time plus 1/2 alpha t squared. And alpha is the slope. Because I have an omega t plot, alpha is the slope. So hopefully that's pretty intuitive. And I see there's a chat. I'll be right there. Okay, so alpha is the slope. And notice it's a negative slope, so you'd have a negative number in there. And omega initial is 5 in this case. So you could do it that way. And I'm going to check the chat. And then, yeah, so let's see. Between 6 and 7. Yeah, probably. I would agree with that. So we see that this part and this part are going to cancel out. And so 2 blocks. So probably right about here, right? You're absolutely right. And let's go take a look at the solutions and see what I said. Let's see. Whoops, we don't want that. Okay, so you're absolutely right. Whoever said that, it will come back again. And so if we wanted to, we could plot that out and see that. I guess the better question in the workbook would have been, at what time does it first return? But yeah, you're right. There's definitely more than one there. Yeah, that was a great question. So Jose asked a very interesting question. If you had this object and it rotates 2 pi, the block would be in the same position, but we would not say it is at the same angular position. The reason why is, what if there was, say, a coil spring attached to this? They're not equivalent, because every time you rotate by 2 pi, the coil spring would have more tension in it. If you don't know what a coil spring is, if you have a garage door opener, or if you've ever seen one, there's a large spring in there. And the idea is, as it twists the number of turns, or sometimes it's called a torsion spring. So, Jose, it depends. Generally speaking, we would not want to assume that. So the answer to Jose's question is, just because something rotates 2 pi, we still assume it's rotated. That way we can count the number of revolutions it's had. And I think we're probably going to do that in one of these problems. I think the next one or something. Yeah. Okay, that's a good question. Hopefully I addressed that, Jose. If I did, just dump it in the chat. Okay. Good question. So I'm reading in the book again. So how far has the mass traveled after 8 seconds? You could just get the areas like I said there. So if you're looking here, oh wait, what did I say? Oh crap. Look at that. How far has the mass traveled? I want to bring that question up. This is a sneaky one. All right. So when you see how far has the mass traveled, that's the letter S. It's not asking for delta theta, but it is related to it. It's the radius times delta theta. And again, think about it. When you read the question carefully, how far has the mass traveled? Well, it's gone around and around. And so you're going to have to split this up into negative and positive chunks. And you need to get all the different delta thetas. I'm going to go into the solution to show you that. The idea is, whoops, there it is. In this case, okay, we want to get this, but total distance travel, that's a sneaky question. I get all of the different delta thetas, and then I get the absolute value of these. And so this will tell me how much angle it is total traveled. This tells me how much angle it is displaced. So I have a total displacement of 10, but a total angular travel of 32.5 radians. And so distance is then R times that. It's sort of like distance versus displacement. If I ask you for distance traveled, you had to add up the areas and then absolute value them before you add them up. Whereas if I asked for displacement, you would just add up the areas and include the plus minus. So, so this is angular displacement, include the minus signs. This is angular distance, and you absolute value. And then if you want distance, that's different than angular distance. You have to multiply by R. We see now why chapter 10 is a little bit tricky. It's not that it's anything different. It's that the wording is so sneaky. You got to pay attention to the wording all the time. Okay. Sketch a plot of alpha versus time. How did I get these alphas? That's just the slope. So first I have a negative slope, zero slope, large positive slope, small positive slope. So we have negative slope, zero slope, large positive slope, small positive slope. So that's how I got that. And you could do rise over run for each section of that. So if you're getting a little faded, my plan is to finish this problem and take a short break. So if you're hanging in there, that's cool. All right, so part D. How do I get A tan versus T from alpha versus T? Oh, hopefully that makes pretty quick sense. All you do is you multiply the plot by R. Okay, in this case, to get from this plot, to get from this plot here, which is alpha versus T, all you have to do is multiply by r. And so notice the units change because you're multiplying by r, which has units of meters. So we get a meters in here. And now the numbers also change. And they get smaller because it was 0.2. So basically divide all the scale by 5, right? Multiplying by 0.2 is dividing by 5. All right. AC versus time is going to be a little bit trickier. So I'll pause for a second. This plot up here is omega. And I know that AC is equal to R omega squared. So it's going to look like this plot squared times R. Again, if I want to plot AC, it's this plot squared times R, which means because you square it, there's not going to be anything negative. There's not going to be any negative. So if I scroll down, whoops. Hopefully that makes sense. We see right here it went to 0, right here it went to 0, but it never goes negative. And then when it's constant, we don't, yeah, so where is that one? When omega is constant, it just takes on a constant value. So at 2 seconds and at about 4.5, it should snap to 0. 2 seconds and 4.5, it snaps to 0. So by making these plots, I think you can really understand this pretty well. And then a total. A total. How do I make a total? Well, I take this plot squared plus this plot squared, and then I square root that. So you get this crazy ass looking thing. There's a couple of weird little kinks in the curve there, but yeah, that's all right. So again, notice this one never goes to 0 because even at this point, when it's at 2 seconds, AC goes to 0, A10 is still some number. And same thing right here and right here. We see that at these 2 points in time, oh, come on now. We see that it doesn't drop all the way to 0. Whoa. Sorry about that. Oh my goodness gracious. So I'm going to stop the screen share for a second and I'm going to see if there's any questions and see, yeah, if you have any questions, go ahead and pop them in the chat. Oh, squaring a plot in Excel, what you would do is does that make sense, Ryan? What you would do is you'd have a column of ACs and you'd have a column of TANs. Then what you would do is your third column, you'd say equal square root of this squared plus that squared, and then fill down. Is that good?
Yeah, that makes sense. But for like
Yeah.
a prop, like if it were
for
to
a
be like a
sketch?
test question or whatever, sketching it, like would you ever have us do that for something like that?
Probably not, but I do think it's worth doing now just to get some understanding. And one of the things you
Okay.
could do, it's easier if it's just one line. Like say, let's look at the example of 10.6.5 on page 57. See how there's a graph there? That one will be a lot easier to do.
Right.
What you could do is you could literally at 1 second pick a point and then just do the squaring by hand and then make a new point. So literally do exactly, so basically you make your own little table and pick a couple of points and literally just square them out on paper and do the math.
Okay.
Because if you read the plot, you should be able to figure out AC and A tan from some other parts of the problem as functions of time. And you can,
Okay.
yeah, cool.
Yeah.
Another thing that you could do is remember that AC is equal to this that I'm writing here. So, whoops, I forgot a paren there, but something like that, right? And so if you have that, what you could do is you could literally, if you know a table, you could just pick a couple of points and do that square right there on the paper. Okay.
Yeah.
All right.
Okay.
Good.
Okay.
Yeah.
Cool.
Other questions before we take a break? And then let's see. Luke, okay, I didn't see your question until now, Luke. I'm sorry about that. For no, I'm not sure what you mean, but hopefully you got your questions answered, Luke. If you did, just let me know. If it didn't, let me ask it again. All right. Oh, okay. I got you. Okay. All right. Sounds good. All right. So I'm going to take a quick break and then we'll come back and we'll do another 45 minutes of hell and then get out of here.